Hi everyone, my name is Haytham Abuelfutuh. I am co-founder and CTO at Union, one of the original co-authors of Flight, the open source workflow orchestrator. Before I get started, I would like to share a little story that happened recently. I think is very relevant to the conversation today. So, see, my wife likes to change our furniture, when we can afford it, and every so often. So recently, we went shopping for a coffee table at Crate and Barrel, and we found what I think is probably the perfect coffee table. It's using great wood, solid, great design, beautifully finished, has a relatively high sticker price. So I had one of those moments where I thought, how hard can it really be to make it myself? And that started probably a 2 or 3 months journey. I went back, started buying materials, buying tools, went back and buying more tools and more materials. And 2 or so months later, and hundreds of dollars later, I ended up with something that looked like that table. But probably you want to keep it in your garage. So what happened next? Of course, I went back to Pit and Barrel, put that same table. I think this is very relevant to conversation today because it's often times we see this working with open source community. Things look a lot easier than they actually are. Serving production LLM code or AI workflows may seem easy once you do it on your laptop on a single machine with very constrained environment. But once you decide to put this out at scale, durably in production, it becomes a daunting task. I've been working in building distributed systems for so long now. I worked on the Flight open source project a few years ago when we were building it at Lyft, then open sourced and worked with hundreds of open source companies that were using our open source product and helped them ship production grade software, production grade distributed systems for AI, for data even, for ML workflows, even for inference. And most recently, at Union, I started working with the team on building and shipping this great inference service. We wanted to make it easy, wanted to make it solid, durable, and runs at scale. And today I would like to walk you through how you can get there. And we'll start off with this maybe simple question. This may sound familiar to you. You start on your local machine, on your laptop, with maybe an Olama server or Llama CPP, one of those, great to run locally servers, and you download the model from Hugging Face. You start serving it on your laptop. You start sending queries or prompts, and you're getting responses. Maybe not the best responses, but that's okay because it's a small model. And you get to a point where, I think this is good enough. I tweaked my prompts and I know how to use this. Let me just ship it to production. And then reality hits. It may be one of those tasks that seem a lot simpler to do than it actually is. It will take you a lot of tweaks, a lot of improvements, a lot of changes. I want to add a cache here, there, and then you end up with a system that's very hard to maintain, very hard to even understand, hard to make changes and further improvements on. And you probably go back and buy that API. Before I get into the process of building inference at scale the right way, I want to show you what we got out of this and why that would be important for you to consider. So at Union, when we built this system, we wanted to build the best inference engine or inference service out there. And I think we got there. It's arguably one of the fastest in the market, even when compared to optimized and benchmarked Anyscale or SageMaker. It's like multiples faster. It's even 5 times faster than Modal. Some of these services tote the speed to get started or to start up as one of their strongest suit. And I think the trick and the fall is that if you're not building infrastructure that's specialized, that understands LLMs, understands the requirements of an LLM, you are bound to make generalizations that will hinder performance. It will hinder the performance you can achieve out of the service. So let's start from the top. Start with a simple design. You grab a machine, maybe an EC2 machine from AWS or some other provider that has a GPU, and you run an engine on it. They start downloading a model from Hugging Face, and you start, serving traffic, start using it yourself, and it's decent. It works, right? But then, given that GPUs are scarce and all, you're probably trying to share resources with other people, or even for yourself to iterate on this app. You are, bringing it down, coming back up. You want multiple versions running at the same time because you want to compare models. Do I like the Llama 4 or a smaller DeepSeek? Or like, which one runs better for my use case? You want to do some testing that way, and you don't really have an infinite supply of GPUs. If you do, I want to talk to you. Then you will probably optimize this by running a scale to zero solution, right? We're not using the model, scale it to zero. When I start hitting it, scale it back up. And very quickly, you will run into these two, say, crucial problems. They're usability problems, they're production problems. First of all, running or getting to a running container is slow. And getting the model on that container is even slower. If you just run back of napkin calculations, you understand that, an image is probably somewhere from 15 to 30, 40 gigabytes. A model is a couple, maybe 100 gigabytes, maybe more if you want a bigger model. And the way all of these services run your containers and models is they run in sequence, right? So you first download the model, first download the image, start the image, and then it starts downloading the model, probably to the disk, to your local disk, then load from the local disk to your GPU, and sequencing these operations will just take a long time. And we would like to talk through how did we solve this. There are, of course, physics limitations here. There are like numbers you cannot optimize from because this is how fast light travels between machines. But I think within that, there are a lot more optimizations that can be done from the status quo. So let's start with container images. The typical way this runs, you're running on, let's say, a Kubernetes cluster, kubelet comes up, it starts downloading the image, container D starts downloading the image. Once it's fully downloaded to that machine, it starts up the container. And only at that point do you start downloading the model. There's a lot of research done here, but the basic premise is that you probably don't need the 30 gigabytes of files in that image. Some research, I think the number is around 80% of the image can probably be discarded and you're fine. You don't need it. For different use cases you may, but you're starting this image for that one purpose all the time, and you probably don't need all of the data in it. So what do? There are few open source projects that try to tackle this, and they have been around for a while. They're not widely used, I would say, because it's hard to get them deployed and get them right. But if you do, you will get a lot of benefits. The basic idea that behind them is you only load what you need. Figuring that out is the harder part. But if I get an image, I can start it up. I can monitor the operating system open operations, file open operations. I can know which blocks are being accessed, which files are being accessed, up to the point where it starts downloading the model, and say, great, let me capture this. I will reshuffle the image so that these files get downloaded first and allow the runtime to start the image immediately. Then the second thing you can do for images, for the container images, is you set up a peer-to-peer network. You don't want to download these images every time from your container store or from the object store, which is, again, physics-wise, further away from the next machine on the rack. So if the next machine on the rack has the image cached, then you should probably be downloading from there first. And the second problem, let's try to optimize how models get on the GPU. The basic flow is the GPU, the model live on an object store, gets through the CPU and the network card all the way to your machine, network card, CPU, RAM, then gets written to disk, then loaded from disk to GPU. All of these hubs are not really needed, right? I have the data there. I want it in the GPU memory. Why can I not do that? There's a lot of research happening right now to enable exactly that. There's RDMA, the GPU direct on top, with that goal, right? So you get data from, let's say, S3 machine memory all the way to your GPU memory with minimum hops. But at the moment, that's not available, right? What you can do now, though, you can cut some of these hubs today. So you don't need to store, you need to load the entire model to disk before you load it to GPU, for example. So you can write custom code that will stream the models. You need to use a streamable format. You can stream the model directly from S3 and push it to the GPU without going through disk. This, with just these two optimizations, just optimizing the images and just optimizing the model load, again, they're very generic, right? You don't need to know what model it is to do it. You can already beat, I would say, 80% of the providers out there that serve models. It's hard to do, and I'm sure they're all working on it. But if you manage to get there, you'll be already faster, and you'll be happy with what you ended up with. However, once you start using the service, you start sending requests, getting back responses, and you will notice that as the conversation gets longer, it gets slower. The first token gets slower, which is odd because, again, if you use OpenAI or any of the API provider services, they don't suffer the same problems. And what are they doing? But to understand this, I think it's worth understanding how the LLM serve your request to begin with. See, the LLMs don't have memory, right? It's essentially a stateless service. So for it to know, I need to add additional tokens to this query, your app needs to send the entire context, right? So from the first prompt, including the responses, the previous responses from the LLM, all the way to the very most recent prompt you sent, get sent to the LLM for it to start generating additional tokens on top. And what it does is it gets every token. So let's say a token is a word, as make an assumption. And we have they love coffee as the context. What will happen is first pass, it will generate what is called keys for each one of these tokens. It will then compute matrices that are based on where that token is relative to the attention window around that token. So trying to figure out how important is this word relative to your context. And you can quickly notice that these values don't change, right? The sort of context is really immutable. Only new tokens get added to. So if you compute them once, you don't really need to compute them again. And if you did any computer science problems or distributed systems problems before, the obvious answer here is let's cache it. And that's what you do. You add a cache onto that machine, and many of the open source solutions serving engines already support this. If you look at VLLM, you look at Dynamo, you look at Zlang, they all have some form of this where you can put a cache next to where your model is. It can cache on the GPU memory, it can cache on the main memory, or even fall back to disk. And the whole purpose of this is avoid computing the KVs for previously computed tokens. And this is great. You get to this point and you start chatting more and more with this model, and you like it enough to compare it to other APIs, right? You start sending requests here and there and just see how do they stack against each other. And very quickly notice that yours is always slower to get to that first token. And it may not be obvious why, and want to go peel the onion a little bit here and understand how GPUs really decide, or the LLMs decide, how do I give you that first token and subsequent tokens. It goes back to an optimization done on these engines to cram all the stages needed in the LLM, like token generation, onto a single GPU, because that's the easiest to start with, the most sort of looks like the most cost effective, but it hurts performance. There are two stages for generating a token. The first stage is called prefill, where it gets to compute all of these matrices we talked about for all the input tokens or the context tokens. And then the next step is the decode, where it like multiplies this by all the weights or the active weights in the model to compute the final results. By combining these two stages in a single GPU, it becomes hard to extract the highest throughput you can get from the GPU, because they have different resource requirements, and that slows down overall generation of tokens. And the simplest solution here, simplest solve, is to split the two operations, right? So you prefill on one GPU and you decode on another GPU. The memory stay sort of constant for each, relevant to the operation it's trying to do, and they exchange data through very fast bus if they land on the same machine. You also have to add a router that knows how to do this, that it calls this to do prefill, get back results, call the other one to do the decode, get back results, and then return the final results to the user. Now, have to be careful how to place or co-locate these GPUs. If they land on different machines, you have to deal with passing. How do I pass data between the machines? There's, NVIDIA Nixel can solve this, and other solutions. You can implement your own. I think maybe out of the current open source serving solutions, only NVIDIA NeMo has that sort of built-in or comes with the engine. And then the next thing is your model gets popular, right? A lot of people are hitting it, and you start thinking about horizontally scaling it and adding maybe more GPUs or adding more machines, and you replicate. The easiest way here is, let me just replicate what worked, right? I will copy the same setup and start up. Since we figured out auto-scaling, it's okay. It will take a couple of seconds to start the new machine, and we'll be ready to serve requests. The biggest problem you will hit here is, how do you decide which machine should serve my request, right? If I land on the right machine, the cache is primed, and I can use previously computed KVs. Otherwise, I have to recompute them, and then I get a very slow response, especially as the context window gets bigger. It's great, no problem. I will add another layer on top that has a smarter router that knows where should I send the traffic based on the request. So it will look at the prompt. It's not a typical, distributed systems router or proxy, because it does need to understand that this is an LLM. There is a query being sent. I need to look into the query and try to match it to the machine that will more likely able to serve the request. You also add a prefix cache, you add a offloaded KV cache, so even if you land on a machine that doesn't have your cache primed, it can copy the values directly from this offloaded cache, because that's still faster to do than to recompute them. Again, particularly for large contents. Looks great, looks complex, but is the right architecture. And by this point, you are probably, I would say, 99% there in understanding what NVIDIA NeMo looks like, what the VLLM production stack should look like, or Zlang will look like. They're all moving in this direction, where you have these boxes so you can serve a production system at scale. They're at various maturity level. I don't think any of them is in a sort of ready to use state at the moment, but they're all marching towards this unified architecture that, regardless of the model, it will do it at scale well. Your next problem is, once this gets very popular, you are running at scale, and you want to then move it even beyond this single region, maybe for GPU availability, maybe for price, maybe just for availability across geographies. So you want to go global. You deploy to multiple regions, maybe multiple GPU providers, and you want some smart layer on top that knows where to send you. The current solutions to this are all based on latency, ping latency, knows like where maybe taking some data privacy considerations. They're very typical high-level constraints that are put on the server, on the router, to decide where to send your traffic. But because these are LLMs, where you send the traffic matters a lot for the performance. So you need a special, smarter router here that knows how to send the traffic or where to send the traffic to based on, again, the cache and where your request was previously sent. Sticky cache, sticky sessions, like many tricks that can be played here so that you land in the right place and the right machine to get the fastest response possible. Now, this is all doable, right? And all of this will add up to quite a faster platform than any that is currently available. At Union, we built this solution, abstracted away all the complexity, and gave you an open book, I guess, for you can peek into how all of this is done. But as an end user trying to serve a model, you want to get a model that works locally to just go to production and have all of this complexity handled for you. And you do it in a way that gives you the best chance to compete really with an API provider that's very optimized from day one. That's all they do. Our users are then able to productionize their AI models, not just their workflows, to production, goes faster, and it's a lot cheaper than the competition. Just a peek onto what Union does, right? We just zooming out. At Union, we're trying to solve this AI in production problem. And this involves running workflows, running the processing for batch processing, batch inference jobs, but also running inference at very high scale and very low latency in production with reliability, durability, all the guarantees you want on one common platform. And that's why we went in the journey of building this inference platform. Let me leave you with this. I think we entered evidence, the writing is on the wall, a new era of models, right? There are models that are being shipped to production every other week. Just before, between preparing these slides and going through them, Llama 4 was already released. It's already beating a lot of other models in a lot of benchmarks. It's a lot smaller, gets quantized and runs a great performance even on your machine. But I think per model optimizations can only get you so far. It's like writing an algorithm and trying to optimize this algorithm a lot and then thinking, well, it's a very optimal algorithm. I can just take it to production. The process to do that is a lot more involved as we walk through and needs a lot of awareness about how LLMs work to do this right. But I think nevertheless, a lot more models will be going to production than ever before. I think a lot of companies will do self-deployed models, and I think it will get to a point where requests served by these self-deployed models will far surpass the API-based requests in probably the next year. I think systems innovation is key. I think people thinking about how to serve requests, how to ship things to production from distributed systems perspective is going to be the differentiator for a successful launch or not. And lastly, I think we should all be working towards democratizing this process. I think it's a lot of work, but I think it's getting to a point where it needs to exist at high scale with very low friction, barriers to entry, make it seamless for everyone to take their models to production. And with that, thank you.